All right, what's up everybody? Welcome to the next video. This one's going to be pretty short because the problem solving portion of the video is going to be a little bit longer. Topic 5 in Unit 2 is over Lewis diagrams, okay? And many of you will have already done this before, and so this first day that we talk about Lewis diagrams is going to be pretty much review for most everybody, I think. We will get into some more complicated things like resonance and bond angles and things like that, which you probably are less familiar with. But Lewis diagrams should be mostly review. So you can see that the learning objective here is pretty simple. We need to be able to represent molecules with a Lewis diagram, okay, or a Lewis structure. So let's get into it. Our table of contents for today, we're going to talk about the localized electron model, which is sort of, once again, going to be review for a lot of you, I think, even if you don't know it. We're going to look at some Lewis structures, the octet and duet rule, mainly the octet rule, and then some exceptions to the octet rule. Okay, and you can find this stuff in your textbook in Chapter 8. Like I said, the problem-solving portion of the video is going to be a little bit longer than this. I'm going to actually go through some examples of how to draw or construct these Lewis diagrams. Okay, so the localized electron model, I didn't even know that it was called this, okay, so I don't think it's important that you know the name of this, but you do need to know what it says, what it's about, okay? So, covalent bonding, right, in contrast to ionic bonding, covalent bonding involves the sharing of electrons, okay? Remember that ionic bonding involves the transfer or like the gain or loss of electrons, right, to form those ions, which are then attracted to each other. Covalent bonding is different, okay? And so we're going to be spending the remainder of this unit talking about covalent bonding, starting today with these Lewis structures. The localized electron model assumes that molecules are composed of atoms that are bound together by sharing pairs, okay, that's important, sharing pairs of electrons using the atomic orbitals of the bound atoms. Electron pairs in the molecule are assumed to be localized on a particular atom or in the space between two atoms. Okay? The pairs of electrons that are localized on a single atom are called lone pairs, and those that are found in the space between atoms are called bonding pairs. Okay? So the sharing of electrons in covalent bonding, it would be the bonding pairs that are the ones that you're familiar with, right? Let's just look at some examples, okay? So, a couple of notes here about Lewis structures before we get into some examples. Lewis structures are just models or diagrams of molecules that show how the valence electrons are arranged among the atoms in the molecule. Excuse me. Generally, molecules form when atoms can share electrons to achieve noble gas electron configurations. So remember, this is similar to when we were talking about ions at the beginning of this unit, right? Ions form when atoms gain or lose electrons to achieve the electron configuration of a noble gas, okay? And it's the same story with covalently bonded molecules, except they just achieve that electron configuration in a different way. Instead of gaining or losing electrons, they share them with each other to achieve that noble gas electron configuration. So, noble gas elements have 8 valence electrons, okay? The exception to that is helium, and we're going to talk about that in just a minute, but all the other noble gas elements, neon, argon, krypton, xenon, radon, etc., have 8 valence electrons, okay? Meaning they have 8 valence electrons in their outermost energy level. When atoms share electrons in a covalently bonded molecule to achieve noble gas electron configurations, they end up with 8 valence electrons. This concept is referred to as the octet rule. Okay, so octet means 8, and so the rule about atoms ending up with 8 valence electrons in a molecule is called the octet rule. Okay, and here's a little quick example. I'm actually going to read this to you guys. This is from your textbook. It's a little bit blurry. I'm getting all of this stuff from Chapter 8, by the way, so if you want to go back and look through this after the video, you might want to do that. It says here, The second row, nonmetals, carbon through fluorine, form stable molecules when they are surrounded by enough electrons to fill the valence orbitals. Okay, and their valence orbitals would be the 2s and the 3 2p suborbitals. Okay, and I don't want this to be confusing. So it's the 2s orbital and then the 2p orbital, but remember that the 2p orbital technically has those 3 suborbitals in it, right? So you can have 2 electrons here in the 2s orbital, and then you can have 6 electrons in the 2p orbital. Those 8 electrons are required to fill these orbitals, okay? These atoms tend to obey the octet rule, okay? So, long story short, pretty much every element other than hydrogen and helium, which I'm going to talk about here in just a second, will obey the octet rule, or will attempt to obey the octet rule. Okay, there are some exceptions. So let's look at this. Let's look at this fluorine molecule, F2. Okay, fluorine has 7 valence electrons. Okay, and so you can see that here. 7 dots are surrounding the F. That's how you draw a Lewis structure, by the way. You just draw the element symbol and then put dots around it to represent the valence electrons. 2 fluorines can help each other obey the octet rule by sharing a pair of electrons between them. Okay, and there's some more examples that I'm going to show you later in the video and in the problem-solving video where we'll see how that works exactly. Okay. Now, I do want to mention the duet rule. I didn't really know people called it this, but it makes sense. Duet means 2, right? So not every element obeys the octet rule. 1 or 2 notable exceptions here are hydrogen and helium. Okay, hydrogen follows the duet rule, and this is because hydrogen only has 1 valence orbital. Okay, so instead of having 2 valence orbitals, the 2s and the 2p orbital, hydrogen only has the 1s orbital. Okay, that's its valence orbital. This can only hold, that should say 2 electrons. Okay, so this would be the valence, or sorry, this would be the Lewis diagram for hydrogen gas, H2. Okay, you've got 1 electron on each hydrogen. They can share those electrons between them. They can share that pair, and then they both have, or both feel like they have 2 valence electrons. Okay, helium is the other exception. It is also a noble gas. It doesn't have 8 electrons. It has 2, but it is still considered a noble gas and doesn't react with other elements because it has that full valence shell of electrons, right? The 1s orbital is full with 2 electrons. Okay, let's look at a few more examples really quickly. And like I said, I'm going to be going into a lot more detail in the problem-solving video. Here's water, okay, so H2O. These would be examples of lone pairs here when they're drawn just as dots, okay? And now sometimes you might see a Lewis structure that looks like this that has the dots there as the bond. Sometimes people will replace the electrons that are shared with a line, okay? And like I said, I'm going to go into more detail on this in the problem-solving video, but I figured it'd be useful to bring that up now. So yeah, these are the lone pairs that reside on the oxygen, and then these are the bonding pairs, okay, the lines between oxygen and hydrogen. Those lines represent 2 electrons that are shared between these 2 atoms here, okay? And as you can see, if you take into account the shared pairs, each atom is satisfied, right, with its valence shell of electrons. Hydrogen has this 1 shared pair. This hydrogen has another shared pair. Oxygen in the middle has the 4 lone electrons, okay, the 2 lone pairs, along with the 2 shared pairs for a total of 8, right? So oxygen is obeying the octet rule, hydrogens are obeying the duet rule. And then you can see that also works with carbon dioxide here, okay? Same sort of situation. We've got an atom in the middle here. These are all atoms that will obey the octet rule. And so carbon has double bonds, actually, right? So each one of these lines represents 2 electrons. So actually, there's 4 electrons here shared between carbon and oxygen, 4 on this side as well. And so each oxygen has 8 electrons, and the carbon in the middle has those 4 bonded pairs, or the 4 shared pairs. And so that's 8 electrons as well, okay? So, like I said, I'm going to go into some more detail when I actually do some examples of this in the problem-solving portion of the video. There are some exceptions to the octet rule. The first thing I want to mention is actually the last sentence of this slide. We are going to look at some examples of exceptions to the octet rule, but memorizing all of the exceptions is not needed. Okay? It's useful for you to know that there are exceptions to the octet rule and to be able to potentially explain why there's an exception or something like that, but you don't have to memorize all of them. Here are some of the exceptions. Okay? Row 2 elements like beryllium and boron can form some stable compounds while only having 4 or 6 valence electrons on beryllium and boron, respectively. Okay, so they don't follow the octet rule sometimes. These compounds tend to be highly reactive, indicating that they aren't as stable as compounds which do obey the octet rule. Okay, another set of exceptions, and actually there's quite a few that can do this. Some larger elements like phosphorus and sulfur, and others, even some noble gases, okay, like some of the large ones like xenon, can form stable compounds while having more than 8 valence electrons. These larger elements have access to d orbitals. Okay, d orbitals can hold 10 electrons, right? And they have their valence orbitals. So they've got space to create what is called like an expanded octet. Okay, it shouldn't even be called an octet really, but it's a stable compound that has more than 8 valence electrons on that central atom. And like I said, we're going to look at some examples of this, but you don't need to memorize all these examples. Okay, in your book, a really great summary of all these rules can be found on page 331. Okay, I would take a look at this. I've got it listed here. I'm not going to read all of this here to you. But if you were looking to memorize something about Lewis structures, these 5 statements here would be something to look at. Okay, this really does tell you all you need to know about Lewis structures. Okay, and we're going to be doing some examples of Lewis structures in the problem-solving video, which I will have up here shortly. Okay, all right. I told you this one was going to be a short one. All right, thanks for watching, and I'll see you in the next one.